Section 6.8, the divergence theorem, one of the three important theorems in Cal 3, which is due to Mr. Gauss. The remaining, the previous theorems which we have learned in addition to this are Green's theorem and Stokes theorem. So those are three crucial theorems in multivariable calculus. Today, we'd like to go over something called divergence theorem. The word divergence, basically it means compression or expansion of a vector field. I will elaborate this momentarily, but let's make sure for now it's compression and expansion of a vector field. The formal theorem of divergence theorem is as follows. Let E be simple solid region and S be the boundary surface of E. Let F be, so this is the third condition, 1, 2, 3, a vector field whose components have continuous partial derivatives, meaning the partial derivatives of this guy with respect to x, y, or x or y and z are, well, they exist, they're continuous. If that's the case, the flux integral, which we learned in previous section, can be related to triple integral of divergence of the vector field over the volume element. Showing in other words, divergence theorem is a relationship between surface integral over vector field and triple integral over the what? Volume of the solid. dV is volume, remember? So in other words, the flux of F across the boundary surface of E, which happens to be S, is equal to triple integral of divergence of F over the volume of the solid. So that's really powerful theorem, which enables us to go back to the previous section and do those some of those flux problems, specifically the ones which you had like multi-surfaces in one shot. So you don't have to parameterize each surface one at a time and add up the results to come up with so-called net flux. So that's really nice, very nice theorem. It's really a lifesaver. So let's quickly define what they mean by solid. Solid means closed surface. I need to repeat that what? If the surface is not closed, like, you know, you have like your surface is a plane or an elliptic paraboloid which has no top on it or lid on it, then you cannot, I repeat, you cannot apply divergence theorem. So divergence theorem only applies to solids, meaning closed surfaces which they happen to be airtight. So what's a simple solid? Well, those are like the type of quadric surfaces, which we learned quadric solids, surfaces, the type of solids, I should say, which we learned in chapter 12. Like what? Like, you know, ellipsoid, rectangular box, and type 1, type 2, type 3 solids. Type 1 is like when the solid stretches along the z-axis, 2 is like along the x-axis, you know, type 3 is like when the solid is stretches along the y-axis. So keep in mind, you got to have a closed surface. It has to be a solid, not just any surface. It cannot be open surface. So let's define open, connected, simply connected regions of a plane. Open formally means what? A region, I should say informally, means the region which does not contain its boundaries. Notice the edges of these regions happens to be dotted line. So these are very open regions. These are closed because notice the edges are drawn with solid lines. This is neither open nor closed. So that's what we mean by what? By open region, which means does not include what? Its boundary. And closed region is what? Includes or contains its edges or boundaries. Then we have something called connected region. What's a connected region? Well, if you select any two random point in the region R, and you draw a nice curve, the entire curve has to lie in the region R. So this is connected, all right. This is connected, all right, but this ain't connected. Why? Because when I select a point here and here, let's say A and B, and I draw a nice curve joining point A to point B, notice portion of the curve is outside of the regions. So this is not connected. What do you mean by simply connected region? Simply connected region informally means what? You have no holes in the region. No holes. So if there is a hole in the region, then it's not simply connected, correct? So we should have no holes in the region, correct? And that's basically what simply connected is, right? In other words, most of our regions will look like this, no holes in it, okay? So why do they call it divergence? Okay, let me just set the scene, then we'll do some problems. The reason they call it divergence, the term divergence come about, informally it means if F represents the velocity of a fluid, remember what fluid is. Fluid, it could be gases or liquids. It's just a general term which covers gases and liquids. Then the divergence of that velocity of the fluid at some specific point represents the net flow from the point. In other words, it represents the net rate of the flux per unit volume at point P. So when you take the divergence of of a vector field, there are three possible scenarios. Either the divergence comes up to negative or positive or zero at a specific point. Like let's say point P. In this case, let's say point P is 0, 0, 0. And let's say this is our vector field. So when you do the divergence, okay, it comes up to negative, right? And that indicates what? You have, what do you have? The fluid flowing into the ball. So these are called inward flow at point P. So the point P is known as sink, just like kitchen sink. In the other case, if the vector fields diverges from point P, let's say this is point P, meaning if the divergence is positive, then we have an outward flow at P, and the point P is called source. So the example of a source in real life could be like heat. Heat, dissipates from a point around to the surrounding, whereas sink is like cold air which contracts, where heat is like expands. So that's called source. This is called sink. Sometimes you have neither sink or source. You have rotation. And let's say this is the vector field which represents that rotation, negative 2y, 2x, 0. In this case, the divergence is 0. In other words, no net flow in or out of the net ball, so at 0, 0, 0, the divergence is 0. In fluid mechanic classes, we call F is incompressible. Okay, what is incompressible? In fluid mechanics, incompressible fluids are the fluids if a force is applied to or the pressure is applied to an incompressible fluid, it does not change its density or volume of the fluid. Such as Such as, let's say, liquids. Whereas if you apply a force or pressure to the fluid and it changes its density or volume, then those are compressible, such as gases. You remember, gases you can compress, liquids you cannot, right? So liquids are examples of incompressible fluids. Gases are what? Compressible. And that's, when the divergence is zero or is not equal to zero. If it is zero, it's incompressible. You cannot change its density or what? Volume. You see it. So with that said, let's do a quick example and see how this works. Suppose, so this is an example, suppose the vector field is z, y, x. Remember what that is. That's like zi plus what? Yj plus what? Xk. That is your vector field. Whatever it represents. It could be the velocity of a what? Fluid. It could be the force. Who knows? Find the flux of F over the unit sphere. Unit sphere means what? The radius is 1. And we like the center to be at 0, 0, 0. So the center we like to be at 0, 0, 0 because of the equation, correct? And it says right here, outward normals. Remember, sphere is a closed surface. So we are good to go to apply what? Divergence theorem. So how do you take the divergence of a vector field? Well, it's a scalar. All you have to do is take the what? What? What is it? Let's call this M, N. Let's call this P. So this would be partial derivative of P with respect to X. Excuse me. Partial derivative of what? M with respect to X, correct? Okay. Plus partial derivative of N with respect to Y, plus partial derivative of P with respect to Z. Partial derivative of Z with respect to X, there is no X here, it's 0. Partial derivative of Y with respect to Y is 1. Partial derivative of X with respect to Z, there is no Z here, is 0. 0 plus 1 plus 0 is 1. So the divergence is what? 1. So the flux integral is the same as triple integral divergence of F over the what? Volume element. In this case, the divergence came up to 1, which is constant. And now you have 1 times this triple integral, right? Remember, if the integrand was 1, when you were doing what? Triple integrals back in chapter 15, this represents the volume of the solid. So I really don't have to evaluate this because I know the volume of the sphere is 4/3 pi r cubed. So I'm just going to say, that's 1 times the volume of the sphere, which is 4/3 pi. The radius was 1 cubed, and lo and behold, there it is, 4 pi over 3. But just imagine for a minute, you were going to do this by what? Direct way using what? Previous chapter's method. First, you had to parameterize the sphere. There it is. Okay, remember in all these cases, rho is equal to 1. You don't see it. So this is like what? Rho sine phi cosine theta, rho is 1. Rho sine phi cosine theta, rho is 1. Z is rho cosine phi, but rho is 1. Correct? You're supposed to do this now. Then you had to take what? 2 partials, one with respect to theta, one with respect to phi, because you decided, or I decided, in this case, theta and phi are what? My parameters, correct? So I have to take the partial of what? The surface with respect to those parameters, and then cross multiply so I can get by what? Normal vector to the surface. But I have to what? Check the sign. Because remember, when you take the cross product of 2 vectors, The direction matters. So when you go partial derivative of r with respect to theta cross partial derivative of r with respect to phi, how do you know this is the correct direction? Why not partial derivative of r with respect to phi cross partial derivative of r with respect to theta? How do you know it's not this order? How do you know that? I don't. But keep in mind, they usually tell you which direction the normal is pointing. In this case, the normal is pointing what? Outwards from the surface, okay? So make sure what? Your normal points out of the surface. But look what you end up with. When you do the cross product, everything comes up as a negative. So you know that's not going to happen, right? Because negatives means what? The normals are pointing inwards, correct? So what we need to do before we take this answer, which has all negative components, right? We need to change the sign. Notice now I change all the negatives to positives. Now I'm good to go. Now I guarantee this guy what? Points out of the surface. Incidentally, what makes you think sine and what? Phi and cosine of theta are positive? Well, remember, um, theta goes from 0 to 2 pi, sine phi goes from 0 to pi, correct? Okay. But this is sine a square phi, so it's positive. And cosine of theta, all right, is what? We are what? We are we are kind of assuming it's positive, right? So keep that in mind. Make sure you check the what signs of the cross product. So just to elaborate of changing the signs is you could pick a point on the surface, and at that point, let's say we pick a point here. At that point, you draw the what? Kind of like three-dimensional axis in the spherical coordinates. And then what? Draw the normal and see for yourself if the normal is pointing out or in. If it is pointing in and you're dealing with outward normal, then you have to change the signs, correct? So that's not it. Now we have to go back to this vector field and what? Express this in terms of what? Parametric equation of the what? Surface, which happens to be what? Here's your x, here's your y, here's your z. So go back here, replace the z with what? Cosine phi, y with what? Sine phi, what? Sine theta, and x with what? Sine phi cosine theta. There it is. Take the dot product of what? Vector field expressed in terms of parametric equation of the surface with the normal vector, ds. Sometimes in your book, well, in your textbook, I think the author uses d sigma. So don't worry about it. It's the same thing, right? So, so now that we what took the dot product, and lo and behold, now this becomes what? dA, which in this case is d theta d phi. Remember, dA depends on your parameters. Because your parameters were theta and phi, so dA or ds becomes what? I mean, dA becomes d theta d phi. And now we know theta goes from 0 to 2 pi, phi goes from 0 to pi to what? Cover the entire sphere. You get the same answer, 4 pi over 3. But get a load of the what? Amount of steps, the number of steps it took to go from beginning to an end versus divergence theorem. This is really nice, folks, really nice. Provided you have all the conditions everything is a-okay, you know, good to go, then you can apply divergence theorem so you can avoid all these horrendous calculations. Not to mention, if you mess up the sign here, the answer doesn't come up right. It'll be opposite of what it's supposed to, right? So the beauty of this, as I mentioned, what? Divergence theorem, when you have multiple what? Surfaces like can of soup. Remember I did this in our live Zoom meeting. So direct way is what? Is parameterize the bottom surface, parameterize the side, parameterize the top, and what? Find the normal vector for what? Each of the surfaces. Apply this formula, take the dot product of the what? Vector field expressed in terms of parametric equation of a surface with the normal vector. And in order to find the normal vectors, you have to what? Take the cross product and check the signs. And lo and behold, what? Add up all those what? Fluxes of S1, S2, and S3, and you get what? The total flux or the net flux is 108 pi. But look what divergence theorem can do for you. Instead of dividing this into what? Three what? Surfaces, because can of soup is closed, right? There's no hole in it, it's airtight. So I can apply the divergence theorem to find the same answer. How? Well, divergence of what? What is it? F, which is this guy, is partial of m with respect to x, partial of n with respect to y, partial of z, what was it called? P with respect to z, correct? So it's a what? It is a scalar. You always get a scalar. It's not a vector. So check this out. Partial derivative of x with respect to x is 1. Partial derivative of y with respect to y is 1. Partial derivative of z with respect to z is 1. 1 plus 1 plus 1 is 3. And that goes and sits right here. Then the double integral, surface integral, becomes triple integral. What? 3 times the volume, but 3 is constant. You can pull that out. And therefore, what's left, which is what? 3 times triple integral, what? dV, this is the volume of a cylinder. And you can pull the formula out of your calculus textbooks and write the formula for volume of a cylinder, which is pi r square h. Remember, the height of the can of soup is 4 units. The radius is 3. So work this out, and what do you know? We got 108 pi. Isn't that beautiful? It's just unbelievably nice. Otherwise, you know you have to add what? The flux on each what? Surface and add them up. Sometimes the students go, well, I'm gonna find the flux at the bottom, and because I have a symmetry, then I'm gonna multiply by 2. No, you cannot do that. We are not dealing with surface areas. We're dealing with flux. In other words, the amount of particles crossing this surface may not be the same as what? The amount of particles crossing this surface per unit time, or this guy. So there is no guarantee that the flux on each surface is the same, so you can use symmetry. So please do not use symmetry for flux integrals. Because as I mentioned, the amount of particles crossing this surface per unit time may not be the same as the amount of particles crossing this surface. What guarantees that? You cannot assume that. So that's my way of saying do not assume what was it? Symmetry. So, so that's basically how these type of problems go. But here is a nice problem, which we will finish this section by. The question is, you are given a surface integral is equal to 72. So here is the flux of F over surface S is 72. What is the volume of the solid? That's really neat, isn't it? So this is like, do you know the relationship between flux integral and what? Triple integral over the volume element. Well, I know this is the same as this guy, and this is the vector field. So I'm going to take its divergent, comes up to 6. So there it is. So I just replace this guy with 6. There it is. Then I'm going to pull the 6 out, right? Then I'm going to end up with 72 is equal to 6 times triple integral dV over E, solid E. But this triple integral represents what? The volume of the solid. Excuse me. So all I have to do is what? Divide 72 by 6. There you have it. 12. So I hope this kind of gave you an idea what divergence theorem is, what does it do, and when to use it. And it's just beautiful theorem. It's just life-saving type of theorem, which I really, really like it. Hope this helped. Thank you.